the talk by Professor Yuri Gliklikh from the Voronezh State University, and he will speak about some applications of stochastic differential equations with mean derivatives. So,
I'll try. I'm ready, but I don't know what about my system.
Please try it.
Okay. Do you see? Do you see my screen?
At the moment, no.
I see. And what to do?
Значит, там есть стрелочка такая вертикальная.
Я стрелочку использовал,
Так.
но я, наверное, случайно вошел сегодня как гость. Может быть, из-за этого?
Нет.
Нет, у вас все права. После стрелочки нужно нажать еще там на что-то, что вы хотите показать нам.
Демонстрация экрана, я нажал, да. А вот теперь, а сейчас?
Сейчас все равно не видно.
Так.
Зато и вас не видно, так какое-то движение есть.
Такое. Но я еще раз нажимаю на стрелочку. Вкладка «Окно приложения», есть окно приложения.
Экран найдите, экран.
На экран, экран. Причем? Окно приложения. Вот а так.
Там демонстрация экрана есть?
Ну, конечно, но я на нее нажал.
Надо кота возвращать. Нажмет куда надо.
А что такое in?
Нажимайте.
На что?
На 1.
In? Так. Ну, я нажал.
Экран 1. Экран 1. Найдите, пожалуйста, рабочий стол слева.
Рабочий стол слева. Действия, чат, команды. Можно на файлы нажать?
Юрий, вы меня слышите?
Да.
Стрелочку вверх видите?
Ну, конечно.
Нажали на нее, пожалуйста.
Я уже неоднократно на нее нажимал.
Сейчас нажали?
Сейчас.
Нажмите на нее, пожалуйста, один раз, стрелочка вверх будет показывать вниз. После этого внизу вы увидите окна.
Демонстрация экрана и in.
Демонстрация экрана.
Так, уже нажимал. Есть демонстрация экрана. Окно приложения или весь экран, или вкладка опера.
Ну, экран попробуйте.
Рабочий стол, нажмите.
А тут его нету.
Ну, нажмите тогда что-нибудь.
Так, ну, я что-то поделиться.
Да, отлично.
Отлично. Это значит... Так, а вот
теперь мы увидели ваш рабочий... Да, презентацию мы видим.
Вот, тогда можно начинать.
Пожалуйста.
Thank you for your kind invitation to participate in this interesting conference. Unfortunately, not personally, but nevertheless, I hope I will explain what I wanted. In fact, when I gave this title, it was in the very beginning, and you see the title includes everything I can say on some applications. I will speak about some equations with mean derivatives, where the right-hand side belongs to some extreme points. I will give all definitions below. So what about mean derivatives? It was this notion was introduced by Edward Nelson for the needs of the so-called Nelson stochastic mechanics, a version of quantum mechanics. Later, a lot of applications of mean derivatives to some other branches of science were found. The main purpose of this talk is to obtain an existence of optimal control for control stochastic differential equations with mean derivatives, whose right-hand sides take values in extreme sets of Hausdorff continuous set-valued vector field with bounded convex images. We prove some special stochastic differential inclusions with the lower semi-continuous right-hand sides that may not have convex images. And they have solutions, and among those solutions, there exists a solution that minimizes a certain cost criterion. By reducing the control equation to the inclusion of this sort, we prove that there exists a control that realizes the optimal solution of the inclusion. It's an analog of Filippov theorem. Notation, sorry. In this paper, we deal with equations in inclusion in the linear space Rn. We use coordinate presentations of vectors and linear operators. Vectors are columns, and if X is such a vector, the transport is row. Linear operators are represented as matrices, you see. The symbol asterisk means transition to conjugate matrix, conjugate operator, transpose matrix. The space of n matrices is denoted, you see, L of Rn. But we need subspace of this space. It's Sn, it's a space of symmetric n matrices. And its subspace, the S plus n, denotes the set of positive semi-definite symmetric n matrices. That is a convex open set in that the whole space. Its closure, the set of positive definite symmetric n matrices, is denoted, you see, with bar above. But my system doesn't want to put that bar over S below. So I don't know why. I will tell about this when we meet it. For the sake of simplicity, we consider equations, solutions, and so on finite time interval. And we use Einstein summation convention with respect to shared upper and lower indices. And what should be said? D over dx is both partial derivative and the vector of basis in tangent space. And for the vector field V and smooth function V, F, we use the symbol VF for derivative of F in the direction of V. And many thanks to RFBR for the grant that supported this research. Now, what is mean derivative? Let on a certain probability space, omega Fp, a stochastic process with values is an Rn be given. We suppose that at every t, the element psi of t belongs to the functional space L1. We denote by p psi t the sigma subalgebra of F that is generated by preimages of Borel sets in Rn under all mappings psi of S, where S is between 0 and t. And by E of p psi t, we denote the conditional expectation with respect to p xi t. And following Nelson, we call it path of the process psi t. Since the audience here is not probabilistic, I have to say some words what is conditional expectation. When we take conditional expectation of a certain probabilistic variable, the result is also a stochastic variable, but it is measurable with respect to that subalgebra, and the integrals over the sets from the subalgebra of this new variable are the same as of the initial variable. So following Nelson, we define the mean derivative, forward mean derivative relative to the past. You see the formula. And the only difference with the ordinary definition is that here we have conditional expectation with respect to the past. By the way, which subalgebra we have to take for conditional expectation depends on the problem. Here we use past, but mainly people take now. It's minimal sigma algebra with respect to which psi of t is measurable. No, and you see the definition. Next, it is, I think it's a tragedy for non-probabilists. In probability theory, they use the notation invented in medieval times. Nevertheless, it's standard notation for the so-called regression. A regression is a measurable finite dimensional mapping such that if we insert psi inside it, we obtain the forward mean derivative, you see. But Nelson introduced several mean derivatives: forward, backward, symmetric, anti-symmetric, and so on. But they all give no information about diffusion coefficient. In order to give some information about a diffusion coefficient, we introduced this new derivative that we call quadratic. You see, it's volume, column, it's row, it's matrix multiplication. It is an matrix. But when we give, but with rank 1, but when we give this conditional expectation and pass to limit, we obtain the symmetric positive semi-definite matrix function on phase space, extended phase space. And for this, we introduce a special lemma. Let it be jointly continuous or measurable smooth mapping from our interval multiplied with Rn to what here there should be bar over S, but my system doesn't want to put it. Then there exists a jointly continuous measurable smooth respectable mapping A, such that this equality holds. So in some sense, it's square root of alpha. And there is a reference. Now consider the Banach space of continuous curves in Rn defined on 0t with usual uniform norm and the sigma algebra C generated by the so-called cylinder set. It should be noted that this algebra equals the Borel sigma algebra on that function space. So we consider the equation with forward mean derivatives with respect to the past. You see, this, the first, it's a system, but we call it equation. The first equation gives information about the drift of stochastic differential equation, and this gives information about the diffusion coefficient. indeed, if we have a solution, then this quadratic derivative equals to, if we take conditional expectation of this right-hand side, it will be diffusion coefficient if it is a diffusion process. For more general, it is not the same, but very close. It's a definition what we call a solution. So it has a solution if there is a probability space and a process with a given initial value. And for almost all t, equation 4 is satisfied. Now, it is not 3 lines, it is capital Psi. Let it be a mapping to some metric space Z. Below, we shall often suppose that such mappings will, with various space Z, satisfy the following condition. For each t, from the fact that the curves x1 and xt coincide on the interval from 0 to t, it follows that psi of t x1 equals psi of t x2. And this fact, in fact, means that psi is measurable with respect to that Borel sigma algebra in Z. A set value for material below, I have to introduce some notions from set valued analysis. So what is a set valued mapping? From X to Y. It's a correspondence that assigns a non-empty subset f of X for X from X capital to Y. F is called the f of X is called the value of X. And for set valued mappings, condition 1 is quite analogous to that for single valued mappings. And consider set valued mapping mappings A and alpha, boldface, that send our extended phase space to Rn and to now bar is here, respectively, and in addition satisfy condition 1. The differential inclusion with forward p mean derivatives is a system of the form. You see, everything's the same, but instead of equality, we have belonging. And we say that this inclusion has a solution with initial value. Is the same if there exists a probability space and a stochastic process such that the initial value is satisfied, and almost surely Xi satisfies inclusion 5. Now, inclusions with a semi-continuous right-hand sides. Here we use some facts from set valued analysis. A set valued fx is called lower semi-continuous at the point x in x if for each epsilon greater than 0 there exists a neighborhood of this x such that from the fact that x prime is in this neighborhood, it follows that f at x belongs to the epsilon neighborhood of f of x prime. F is called low semi-continuous. It is low semi-continuous at every point of x capital. But we will deal with lower semi-continuous mappings. But sometimes we have to use the notion of upper semi-continuous and Hausdorff continuous. You see the definition of upper semi-continuous, that is vice versa. From the fact that x prime from this neighborhood, it follows that f at x prime belongs to the epsilon neighborhood of f at x. And f is called upper semi-continuous on x if it is lower semi-continuous at every point. And a set valued mapping is called Hausdorff continuous if it is both upper and lower semi-continuous. Let E be a separable Banach space, a non-empty set Y in L1, you see. L1 mappings from a given interval to E is called decomposable if the following relation give, you see, we divide the curve into intervals, and nevertheless they are well defined. For every measurable subset Y, where X is a characteristic function of the corresponding set. And it is a particular case of the Freshkovsky-Bressan-Colombo theorem. Let psi D be a separable metric space, X be a Banach space. Consider the space of L1 mappings, you see, which mappings, of integrable maps from this interval into X. Here, B is Borel sigma algebra, and lambda is the normalized Lebesgue measure. If a set-valued map G, C, look from Xi to Y, that is Y, is lower semi-continuous and has closed decomposable images, it has continuous selector. It is very strong theorem. Remark, below we are using only deterministic initial values, i.e. the initial value being a point in Rn, for simplicity. Theorem, let a set vector field R, A, you see from what to what, below semi-continuous, have closed images, uniformly bounded, i.e. this inequality holds. And for all A from the image, set-valued image, and satisfy condition ID. Let alpha be single-valued, continuous, and satisfies condition ID. We also suppose that there exist constants, you see, such that the following inequality holds uniformly. Then under the above hypothesis, the inclusion for, oh, good Lord, for initial condition, this has a solution well defined on the entire interval. Here, a key assumption is that alpha is continuous, because if it is not continuous, here we replace this with some equation where in this place there is a measurable single-valued function, but if it is continuous, then the solution exists. If not, it's a problem. But you should know that since it is an inclusion, then the solution is not unique. And we introduce cost criterion. So there is a continuous function, real valued here, and we consider its integral by dt, oh, good Lord, and then conditional expectation. So for every stochastic process, we obtain a number, real number. And we could show that among the solutions of this inclusion, there exists a solution that minimizes this criterion. Now, the main problem of this talk. Definition. A point Q small in a convex set Q capital is called extreme if there does not exist an open interval of a straight line in Q capital that contains Q small. And say in if it is, say, a square, there are only 4 extreme points. Now consider a set-valued vector field Q and denote by X Q the set-valued vector field whose values at all t and x consists of the extreme points of Q. Lemma. For a set-valued, bounded, Hausdorff continuous vector field Q with convex closed values, the set-valued vector field X is lower semi-continuous. Below we are dealing with two inclusions, 8 and 9. This is you see, it is Q, right-hand side. Alpha is the same as above. And here we deal with the right-hand side consisting of extreme points. And alpha again is above. Under the hypothesis of existence of solution theorem for 6, there exists solution of 8 and 9. And by lemma, it's another problem with my beamer. It can show references to, say, lemmas, theorems, and so on. But it doesn't put these numbers in the definition of this lemma. So I have to say lemma on page 21. Among those solutions, there exists the one optimizing 7. You remember this lemma. Now, control system with feedback control. It is the system of the type. First, it is forward mean derivative with respect to the past. Here is right-hand side of an equation where time and stochastic process and control. Second, it is a line with a quadratic mean derivative. And the third, it's the inclusion for control. So there is set-valued space of controlling parameters, U, that sends our extended phase space to K. It's mean in compact sets of Rm. So the dimension of controlling parameters is another with respect to the phase space. The solution is a pair, solution and control, that consists of a process Xi and control U satisfying inclusion 10. There is a standard procedure that reduces equations of type 10 to inclusions. Namely, on introducing the set-valued mapping, you see, we consider the right-hand side in the first line, but instead of concrete U, we set the whole set of controls for this T and for this curve X. And one can pass from this to this inclusion. Evidently, every solution of 10 is a solution of 11. We shall suppose that inclusions 8 and 9 are obtained by this procedure from equation of type 10 and show that there exists a control that realizes the optimal solution of 9 obtained in lemma on page 21 again. At the optimal solution of the corresponding controlled equation, an analog of Filippov theorem, we suppose that Q is a bounded Hausdorff continuous set-valued vector field with convex closed values, so that lemma, another lemma on another page 22, that the set of X is lower semi-continuous. is valid for this situation. Now, by the way, we have used this notation. Nevertheless, two topological space and X and Y, symbol C denotes the set of all number closed sets in Y, and K compact sets of topological space Y. A set-valued mapping from X to Y is called closed if its graph in this multiplication is a closed set. This means that for any sequences xk in X and yk in Y, such that xk tends to X and yk X to image of xk belongs to the image of xk, and those yk tends to Y. Then the inclusion Y, the limit of yk, belongs to the image of the limit of xk. Set valued f is called upper semi-continuous, and if it's upper semi-continuous and y regular, then f is closed. Let the set valued mapping f sub naught from X to C of Y be closed. The set valued mapping f1 from X to K of Y be upper semi-continuous, and the intersection is not empty at every X. Then the intersection of f sub naught and f sub 1 from X to compact subsets of Y is upper semi-continuous. Let the set valued mappings f, you see from what to what, be closed, and the mapping G be continuous. It's a single ventured. Suppose that for all t there exists U of Tx, curve X, in Rm such that this G of T of curves belong to the image of mapping F with this control. Then the z-valued mapping gamma, you see from what to what, its definition of gamma, is closed. Theorem. Let Q be set-valued bounded Hausdorff continuous mapping with closed convex images, satisfying condition 1 and obtained by the above procedure from the controlled equation of the type we saw above. Let also alpha be the same as the existence of solution theorem for 6, and the set-valued mapping U be upper semi-continuous. Then for any solution psi of 8, there exists a Borel measurable control such that under this control, the process psi is a solution of this equation. Now let's consider the controlled equation where under the control, the right-hand side takes values only in extreme points of Q. The right-hand side with control of such equation we denote like this. So, corollary from the above results. Let the extreme points of all values of Q be obtained by the above procedure from the controlled equation this, where alpha is the same as in the existence of solution theorem for 6. And the set-valued mapping is upper semi-continuous. Then for any solution psi of 9, you remember its inclusion with extreme right side, there exists a Borel measurable control such that under this control, the process psi is a solution of this equation. In particular, the optimal solution of 9 that exists by lemma on page 21, there exists a control such that this solution is realized as an optimal solution of 14. The assertion follows from the fact that any solution of 9 is a solution of 8. Now, I think I see that at the beginning I was talking very quickly, so it's practically enough. In references, I included only several papers. First of all, it's pioneer papers by Nelson, and my papers for which we have references in the text. In particular, all preliminaries can be found in this monograph. This is, in fact, joint result with Olga Zheltikova, and it is accepted into the journal Applicable Analysis, and it is given online at the moment. You can look at it and buy it. Unfortunately, the paper version will be published later, and after that I will be able to send you off prints if you want. Thank you for your attention, and sorry for that I lost 25 minutes.
Thank you very much for an interesting talk. So probably there are questions. I have one immediate question. So you were talking about the existence of the solution and control. Are there any kind of representations for solutions? Some integrals? Are they available?
I don't know. It's a solution of, in fact, it is a solution of stochastic differential equation. And so if you obtain those pair, for example, those pair, then inside substituting the control, you will obtain ordinary stochastic differential equation in eta form.
Okay. Thank you. So there is a question from Yaroslav Granovsky.
Yes.
Okay. Thank you. Do you know the similar results for the ITOS equations?
Which equation, sorry?
ITOS.
Ito.
Ito. Yes. Yes.
Yes, but I probably had to say what is the advantage of mean derivatives. For applications, it's much easier to find equation or inclusion in mean derivatives than in a classical integral form. And here it is not obvious, but there are such interesting mean derivatives symmetric that are called current velocities. And it turns out namely current velocities are analogs of ordinary physical velocity for deterministic processes. And it is most interesting and complicated problem to investigate equations and inclusions. But here it was interesting for us to consider inclusions whose right-hand sides are not convex. Since if they are convex, then it's obvious that it can be reduced to equation, and so on and so on and so on. But when it is not convex, then we have to use that Freshkovsky-Brisson-Colombo theorem, and the explanation becomes much more complicated. Yeah. Since I did not show the proofs, of course, you cannot understand that it's more complicated. Thank you.
Thank you.
Okay. Are there questions? So it doesn't seem to be the case. Then thank you very much again.
Thank you very much. Okay.
Now we